Dr. Lyman is speaking on concentrating urea from simulated urine for use as a plasticizer in regolith-based cement. And she is with Louisiana Tech University, so feel free to take it away.
Bearing with me, I'm the program chair of the Chemical Engineering Department at Louisiana Tech University. And one of the perks of living in Louisiana is that you get to have your internet cut out from time to time, unexpectedly. But thanks for bearing with me and letting me do this later. I want to acknowledge my graduate student, Lauren Mechalip. She did most of the work on this. I mostly was supervising her. Could we go to the next slide? So, Lunar Regolith, we got our regolith from Exolith, which we think is a wonderful company. So thanks, Parks, for working with Exolith. And as you all know, Lunar Regolith has some of the same components as ordinary Portland cement, so it has cementitious properties. Next slide. And what we are interested in is using regolith-based cements and finding a good super plasticizer for it. So what super plasticizers are, they're also known as high-range water reducers. Basically, if you have cement, you can take super plasticizer, put it in the cement, and then you don't have to add as much water to the cement to get the same strength. And this is very important, obviously, for use on the lunar surface because you have a limited water supply there. Often it can reduce the amount of water you're going to need by 30 or more %. And you can see the chemical structure of a particular kind of super plasticizer. If you look at the top thing, you can see that what happens is these super plasticizers have ions in them. They surround cement particles and separate them. And if you have the cement particles separated more, you're able to get a higher strength structure from them. So that's kind of what super plasticizers do. Next slide, please. And so what we are interested in is saying, okay, we know that astronauts are going to produce urine. And so we wanted to try was direct contact membrane distillation in order to concentrate the urea in the urine and then also produce from the urine potable water that could be used for other processes. So if you look at the diagram, you can see what happens is you have a hot stream of what we use synthetic urine, which has a number of different compounds in it. One of the major ones is urea, however. And you have a hot stream going on the bottom, and then you have a hydrophobic membrane. The water vapor is able to go through the hydrophobic membrane, and it goes up to the top where there is a countercurrent cold water stream, and then it condenses in there. The urea and the other components in urine will stay on the bottom because they are not hydrophobic, and so they won't go through the membrane. They're also bigger than water molecules, obviously. And so what we are interested in is, could we take synthetic urine, concentrate it to get more urea, and also get out potable water, and then use this synthetic urine, concentrated synthetic urine in cement. And so, next slide. What we did was we did a 30% lunar regolith and 70% ordinary Portland cement mixture. And we tried different ways to see how workable or plasticized the cements were. To figure out how workable cement is, typically you have what's called a slump test. Now, a slump test has a big metal cone. You put the cement in there, and then you just lift the cone off, and you see how much the cement slumps down. The more it slumps down, the more workable the cement is. And you need to have a certain amount of workability in order to mold the cement to where you want it to be. We didn't have enough material to use a big metal cone, so we 3D printed a small cone, and we would pull that off and see how far the cement spread to determine how workable the mixture was. We used two controls in our study. We used deionized water, and we also used just non-distilled synthetic urine as our two controls. All right, Next slide. And these were results from direct contact membrane distillation. We used in this test simulated urine, and we tried it at the cold stream being at 10 degrees C, the hot stream being at 40 degrees C, or being at 70 degrees C. The nice thing about direct contact membrane distillation is instead of just distilling water off or boiling it essentially, which you have to do at 100 C typically, you can use lower temperatures, and waste heat can often be generated from other processes for these temperatures. So you can see what kind of a flux rate we got with our Teflon membrane, PTFE, laminated membrane, that's hydrophobic. For these two different temperatures, of course, the higher temperature, there were more milliliters per minute per meter cubed of the membrane. Next slide. Okay, and so these are the results from our workability test, our slump test. You can see that deionized water had a less of a slump area. In other words, if you just put DI water in the cement, it wasn't as workable as if you put in either the concentrated synthetic urine or the regular synthetic urine. They gave you more workability. Next slide. And so in conclusion, obviously higher temperature, you have a higher vapor pressure difference, so you get more flux across the membrane. The addition of urea appeared to increase the workability of the cement batches. Although slump is not a very exact test, as you can imagine, you could still tell a difference between the two, having urea in there and not having urea in there, as in deionized water. If you were to use urine in place of water, you could reduce the amount of water you would need. And it also would produce potable water from urine using a relatively low temperature heat source. Next slide. So in future work, we're going to look a little bit more into what concentration of urea were in each of these solutions. We're also going to look at compressive strength testing and also porosity testing. And we also are planning to do curing of the cement under vacuum to see how that would be different. One other thing we're going to try is for direct contact membrane distillation. It will be different in a different gravity sort of situation. And so that'd be something we'd like to try, although I don't know if we will get to that soon. Next slide, please. And I want to thank the NASA La Space for funding for this project. Also, I would appreciate the help of people at Louisiana Tech. And if you're interested in collaborating with me or have any questions about this, feel free to email me at lynam@latech.edu. And thank you for listening.
Thank you very much, Joan. That was at least for me, that was worth the wait. I had a question about the use of the super plasticizer to reduce free water, and you answered it in your conclusion. So, we are in the process of testing a number of different lunar-based concretes with binders that can be extracted from regolith, things like calcium sulfoaluminate, magnesium oxychloride, and we're curing those in reduced pressure environments to characterize the effects on mechanical properties as the pressure goes down. So, might be interested in talking with you about your planned lower pressure tests.
Mm-hmm.
So thank you very much